Good afternoon, everyone. Thank you so much for staying with us till now. Right now, we're going to have a talk titled as LLMs for Revolutionizing Credit Risk Assessments. And we have two wonderful guests, Josh Peters and Kiarash Shamsi. Without any further ado, I will go over their bio. Josh is a data scientist manager at Wealthsimple for the last 2 years. He has led the development of the company's first credit risk model and created a data pipeline to support new credit products. Prior to Wealthsimple, Josh spent more than 7 years working on a data science problem in the insurance, banking, and fraud space through his time at Accenture and Airbnb. Josh's education background is in finance, statistics, and computer science. Kiarash Shamsi is a PhD student at the University of Manitoba and currently working as a financial ML researcher at Wealthsimple. He has published as a first author in conferences such as NeurIPS, iClear, and ICBC. His research interests are large language models, temporal graph learning, graph neural networks, topological data analysis, and blockchain data analysis and systems. So please help me by giving them a warm round of applause.
All right. Good afternoon, everyone. Looking forward to talk to you guys today about LLMs for revolutionizing the credit risk assessment. So I'm just going to give you guys a bit of an introduction and some context before we jump into the details of the work that Kia and I have been collaborating on. So before we get into our actual application, I'm just going to kind of walk you through a brief history of credit risk modeling for those who aren't as familiar with it. So you can actually trace back the kinds of models that are used for credit risk modeling all the way back to the 1940s, when something similar to the weight of evidence scorecard methodology was actually used by Alan Turing to crack German codes in Enigma. He placed different weights on different patterns that he thought might be more plausible, and that was part of the way he was able to build his models to crack the code. And in the 50s and 60s, you start seeing some basic early credit scoring systems come up. You can see an example here, really just dependent on the information that somebody would have with them when they walked into a lending institution, some basic rule sets that are used to determine who is more or less risky. But then in the 1970s, I'm sure you guys all know about the credit bureaus. We introduced the credit bureaus, and now lending institutions had the ability to look at your credit history across other lenders. That was the first time they had access to that data, and that allowed them to build some more powerful models, some more powerful scoring systems, and that's when you start seeing the traditional credit score coming in the 1980s, and that's the credit score that resembles what you guys would all see today, the score between 300 and 800 using some of those basic statistical techniques. And credit risk modeling has benefited alongside the rest of the data science and machine learning industry from the 1990s until now. With the advancements in modeling techniques and computing power, credit risk modeling has been scaling alongside that. There are some, regulatory constraints that would have, made them maybe move a little bit slower in some areas, but for the most part, they've been moving alongside the modeling techniques that have been advancing over the last 30 years. So why is credit risk modeling so important? So what it does is it really is a great risk management tool. It helps you predict and manage the potential losses from default. So the better you are at giving more credit to low-risk people and less credit to high-risk people, the more you can prevent potential losses from defaults. And byproduct of that is helping with capital allocation. So when you know how much you're confident about how much you're going to be losing, you can more effectively allocate capital to other projects. And as I mentioned, there's quite a bit of regulatory compliance in this space. So there's a lot of guidelines that we need to follow in terms of what the bias of the model and in terms of what data can and can't be used in the model. And so we have to make sure that we're following these guidelines when we're developing models in this space. And lastly, credit risk models are one of the few models that have an actual direct impact on the bottom line, on profitability. So the better a credit risk model that you build, the more you'll reduce your bad debt, the more that you'll be providing more loans that have a lower probability of default. So talking a little bit about credit models, what does that really mean in practice? So we start with a set of information like any model. We have application information from somebody, what they tell you as they're applying for credit. And I'll just skip to the right here. We have maybe some internal data like your digital footprint or your client profile that you might want to use as well. But the biggest data source, and the one that we're going to focus some time on today, is the credit bureau data. So you put all these data sources into a machine learning model of your choice. It's a binary classification problem, and the binary target normally looks something like you have a bunch of data as of the time of a credit application, and then you have a target that says, will this person default in the next n months? And when you build a model against that, you end up with the probability of default. Is what are the chances that this person's going to pay me back? And we don't just use that probability by itself. We then use that in conjunction with a couple other dimensions on our what's called a credit policy grid. So an example here is another dimension could be revenue. So we have this probability that says this is the chance you're going to pay us back, and then we have another model that might say you're a high or a low revenue client, and we use maybe those two dimensions to say, well, if you're high revenue and low risk, we'll give you the most credit limit, and then according to that matrix, we'll decide what limit you get, and we'll decide whether to approve or decline you. So that's how credit models are really used in practice. We're going to focus a little bit more on the bureau data side. So what is credit bureau data? I'm sure all of you are familiar with maybe your own credit scores, or that there is some data reported to the credit bureau, but what do we actually receive as credit risk modelers from the bureau? Well, first we receive the raw records. So this is just a raw text file with a series of codes and dates and words, and it's not really human readable without some system knowledge. So you'd have to know like the delimiters, you'd have to know a lot about that specific file. That can be aggregated into a readable credit report. It can be aggregated into something that somebody with domain expertise in the area can understand. There's still a lot of domain-specific codes and language. It's very jargon-heavy. It's not easily modeled in that form. And then what the credit bureaus really sell, what's most useful for our current models, is bureau data in aggregate form. So from that raw report, we can aggregate features that can be easily understood in models. So for Josh Peters, we might say, how many credit cards does Josh have over this past year? Has he defaulted in the last 5 months, yes or no? And those are the kinds of features we use in more standard credit risk models. And to dive a little deeper into that, what is that data? So you think of your own credit history. It's a series of events. It's a series of timestamps, right? When you opened a loan, when you paid a loan, when you applied for a card, when you applied for a mortgage. It's a series. Your credit story is a series of time-stamped events, temporal data. And what the bureau does is they organize these temporal events into what they call segments. You can think of them as kind of panels and different groupings. So for example, loans could be a segment, and you have your whole temporal story for loans. When you opened the loan, when you paid them, when you closed them. And for inquiries, so applying for credit, you have all of your timestamps around those activities, when you had those inquiries, and so on. And there's metadata associated with each of these segments. So for the loan segment, we might want to know how big was the loan, who was it from, what was the payment frequency of that loan. For the inquiry, we might want to also know what industry it's in. Also, who was the inquiry with? And you can imagine that there's several more metadata fields associated with each of these segments. And there's a lot of segments. The segments, there's about a dozen or so segments. It's rare that new ones are introduced, but it can happen. So you think of loans, you think of inquiries, things like collections, things like public records, bankruptcies, your addresses. Each one of these are a series of temporal events associated with your credit history. And together they make your credit story. And all of these are temporal. They all have timestamps. And they have everything associated with temporal data that you wouldn't want to see as a data science modeler. They're asynchronous, so they don't all happen at the same time. They're imbalanced, so not every temporal record has the same amount of events. And they're uneven, which means that there's not an equal space of time between the events. They're also sparse. Someone might have a lot of collections records, but that's quite rare. Most people, that collection segment will be totally empty, so there'll be really sparse data. And they're also mixed type. If you remember the slide I just flashed up, there's integers in there, there's percents, there's strings, there's nominal data. Every single type of data you can imagine is associated with each of these events. So from a modeling perspective, it can become difficult. So as I mentioned, what does the bureau do? They sell aggregate convenience features. So for each segment, they've come up with a series of aggregate features that they believe are relevant to that segment. So for loans, they'll give a certain amount of counts, number of X events in Y months, averages, maxes, and so on. And so you can see features like, number of card loans or number of inquiries in the last 3 months, 6 months. They might choose different time grains for you. And they yield dozens of these per segment, and it can result in thousands of features, but it's still a fixed amount of features based on the logic that the Bureau has decided. So the question is, what are the limitations of that? Well, that means we have to spend some time figuring out what features are most important to us, to our use case, and every lending institution has to decide that. And that's a combination of some statistical analysis and some expert judgment. And it means that if you want to build a good model and be able to detect if it's drifting and monitor it properly, you can't really use that thousands and thousands of features and do that effectively, or it would be really hard to. So you might have to use a limited scope of variables. And it can be really hard to capture complex relationships in this temporal data. There's a lot of highly correlated variables. There's some relationships that traditional models might not be able to understand. And if you choose the wrong feature set, well, then your model can be more susceptible to over or underfitting. So the question is this the best way to do this? And do the credit bureau features capture all of the information? So in theory, they could, but in practice, that's quite difficult. So if you think about a modern sequence model, like an RNN, call it G of X, it can actually generate an infinite number of aggregate features based on that raw bureau report. It can take a look at that raw bureau report, and it can generate tons of features. Might not all be interpretable, they might not all be relevant, but it can do that. And if you think of the features that the bureau provides, maybe f of x, right? Their function on how they determine the features is based on their custom business logic, based on their industry expertise, what their client wants, right? But our hypothesis is that there might be some information lost in that process. The bureau features that are provided, the aggregate features, might not have all the information that's inside that raw credit report. And the hypothesis is that difference of information, that information that's lost between f of x and g of x, could actually result in a much more powerful credit model. So if we're able to tap into that information that's lost, we have a potential to build one of the more powerful credit risk models in Canada. And with that, we started our idea of maybe modeling the vernacular of the raw credit report. So with that idea in mind, I'm going to pass it off to Kia, who's going to walk you through some of our methodologies and thoughts around that process.
Thank you. So hello everyone, I'm Kia, and now you have some idea on what's going on in this credit ecosystem and the data. So let's dive a little bit deeper in what is bureau language model and what is our definition of these models and what we want this model to do actually for us. So here in this section, we have the traditional way of credit risk modeling that we have. So we have the raw report that Josh explained. Then we aggregate some of this information and get some feature out of that. And then on top of this feature, we can create a machine learning model to learn something and then give you a score for the credit. So the problem of this thing is it has a hard process to get this feature. So you have lots of features here. And you can also extract, let's say, I would say infinite number of features out of this credit report. And this is really time-consuming process. And you don't know even which feature is more important. So what we want to do is, why we put that much resource and effort to do this aggregation things and get like all of these things. So we can train an agent. And this agent can go and take a look at this raw data and find out which part of the raw data is more important and extract some features out of that and see like how can we predict this model better. So what we want to do and what we want this bureau model to do is a very abstract thing here. We want to pass the credit report data to a bureau language model, that's the term that we use to describe this model. And this bureau language model should map the raw data to a latent space. It can be lots of dimensions here. So this is just an example of 2 dimensions. And then based on this latent space, we can describe this, let's say, customers or person that we have like the raw data for. And then we can classify the chance of default or any other classification that we want to do on top of this latent space. So this is the definition of bureau language model and what we want to do. And LLMs are somehow magical things here. So it can look at all of this text and extract what we want from all of these features for us. So this is a very abstract system overview that we have. So we want to pass this raw data to an input processor because as Josh said, so the data is not like a very straightforward text or NLP or something. It has lots of jargons and it has lots of codes and it's not even easily human readable. And then from output of this input processor, we want to have a bureau language model and probably fine-tune that. So for this domain-specific problem, and then at the end of the bureau language model, we get that latent space that we was looking for, and then we can do the classification for different downstream tasks, specifically here for the chance of default in the future. So let's look at each single step of this abstract model, and then I will explain you how can we like go deeper inside that and what are our options and what we did so far. So for looking at the input processing, first we need to look at the data itself. So the data itself is something like this example, and as you see, you can't even read that. And this has lots of codes, it has lots of jargons, and if you want to even read this, you need to train your brain to understand like what's going on here. And then how you expect like the LLM to capture this, like the pre-trained model specifically. And these texts, these are mostly numbers. So what you need to do, so to deal with this data and process the input. So you have three options here. First is the traditional way that we have right now that create a custom aggregation. And this custom aggregation can go and take a look at this data and get some features out of that. And then you can use these features to train your model. And this is what we have right now. It's a very heavy process. It needs lots of resources. It needs time. And it also needs a very big domain expertise to look at these things and get the best features to train your model on top of that. So what is the next option? The next option is create a custom tokenizer for that. So you can create a framework or something and pass this text to that and get some tokens out of that. And these tokens is what you can build your model on top of this. And this tokenizer can understand the language of these bureau reports, this raw data. This is also another options that you have, and you can go with that. It's a little bit hard. I will explain in the next slide. And the third option is going from the opposite side. So you have this, and what if you convert this non-readable language to something that's in plain English, and human can understand that, and also the language models, the LLMs, can also understand that because they all pre-trained on English texts. So first take a look at the second option, the custom tokenizer, if you want to go with that. So it's let's consider it as a black box. You pass the raw data and you get some vector of tokenized data out of that. So to define this, you need to first define a vocabulary. So what vocabulary do we have in this specific context? And then you need to adjust some rules for this whole ecosystem. And then you have lots of special tokens and different cases that you should deal with. And it's not like, because it's very domain specific, it's not that much easy to create a custom tokenizer. So it can take lots of time. And also, another thing is, if you want to use a pre-trained model, so these pre-trained models are trained, they have been trained on some pre-trained tokenizer. So you have this model tokenizer, then you get the output, and people pre-train this model on that. So if you want to have your own custom tokenizer, you need to start doing a very big fine-tuning on this model that you have right now. So these are two really big challenges to create your custom tokenizer. But we have a third option as well. So we created a concept here called credit story. And what is credit story? Credit story is a human readable credit history of you. So you have like that, let's say, ugly, unreadable data. Then you pass this raw data to a credit history generator. And at the end of the day, you get something like that everyone. And even if you look at that, you can easily read that, and you have like the whole logical segments in a very clean way stick together. And now you have like a credit data that is readable, even by people or by LLMs that has been trained on this plain language, English language. So this is what we have for input processing, and so far the credit story is the option that you have with less effort, less resource, and you can put less time to go with that. And then now you have like all these credit stories, and these are in English, and you can use the LLM. So now how do you want to go with the bureau language model? So the second part of the abstract pipeline that we talked about before. So here again, you have three options. You can use some text embeddings. So now you have the text, and this text is in plain English. You can use some pre-trained text embedding libraries. So these libraries easily embed the whole text that you have in, let's say, a latent space, and then you can use these embeddings. The second option is you can go with popular generative models that you have, like GPT or Llama. And the third option is go with BERT families or encoder models. So we did some research in all of these three options. So the first is pre-trained text embedding. So the whole pipeline is something like that you have the raw data, then you convert it to a story, and then you have some pre-trained model like this all mini LM that we tried, and then you get your embeddings, the latent space that I explained before, and do a classification for get the chance of default. This model is really easy to implement. So this is a very big pros for that. And also, it's not complex because you're not doing anything fancy here. And it can capture the basic bureau language because you have now the plain English text, and these models are pre-trained on also English text, so you can capture some logic out of that. But the thing is, the performance is poor because these models are not domain specific, and also they are somehow designed for a very general purpose of encoding. So these models should cover like very broad space. And also pre-training phases, it was very small. So they trained these models on less amount of data. So these are the cons of that. And also compared to the benchmarks like LLMs, the big ones, they are performing poor also in this context. So this is not a good option for going with, maybe. And then we get to the two strong options that we have here. The BERT family, like the whole BERT ecosystem, and then the generative AIs that people are talking about. But before I'm getting to this slide, the thing is that generative AIs like GPT and LLM, they are not always somehow a magical things that you can use. So you should somehow care about that. So you not always just blindly go and choose, say, okay, GPT will help us. So this is not the case, specifically for these specific domain-specific problems. So here is the thing. In GPT, if you use GPT or Llama, the thing is these models are somehow designed to be generative. So you prompt something to them and you get something out of that. And these models, these models have been trained on a very massive data, like huge data. And you need lots of data to also, again, tune this for your context. And also you need really big resource to also retune this. And the thing is, you don't have that much easy access to the embedding space of these models to do like the classification and then maybe explainable AI or something if you want to do at the end of the day. But the good thing is BERT family, if you use this family of algorithms, the thing is that these models has been designed to be context aware for understanding the language. And this is what we want to in this context. We don't want to generate anything. Like we don't want to pass some text and get some prompt, passing some prompt and get something out of that. We want our model to understand what is going on in this bureau report and then classify like this customer for us. So also BERT is lightweight, like it's more lightweight compared to GPT and Llama, and this difference is huge. Like you have GPT is really big, BERT is not that much. Also, this BERT needs less data to be fine-tuned for this specific task. And also, the last thing is we have pretty straightforward access. Oops, sorry. We have pretty straightforward access to the embedding space. So these things makes the BERT family better option for this task. But also BERT family algorithms has some challenges as well. So the first challenge is these models, like the pre-trained models, they have been trained on some data sets. So they can be on Wikipedia data, they can be on some academic text. So when you want to use these models on a very domain specific task, the more similar that your target is to the space that the model has been trained on, the better performance you get. So here again, you have three different options. Always you have three options. So in this context, one option is use a pre-trained model, BERT model that has been trained on a close target as you want to use this model on for a specific domain. Like if you want to use this BERT for a financial domain, you need to go with a BERT that has been trained on some financial texts before. The second option is you just train your own BERT, and the last one is get one BERT and just fine-tune it for your context. And the second challenge here is most of the BERT models they have some very limited fixed length token input. So specifically for most of them 512. So again, here you have another three options. You can just use the first part of the text. So let's say you have a credit story, you can just take the first split of the text with 512 tokens, or you can use a BERT model that look at the whole data in a one, let's say, sequence, or you can split the data in different chunks and pass this to your model, like in separate, as separate chunks. So these are all the options that you have here. And the last thing is now you have like the story generation. You know that how this bureau which model can better fit the bureau model place. And now we have the classifier section. So in classifier section also you have lots of different options in front of you. So these are three options that we tried. So the instant pooling, the global classifier, and the local classifier, and we have lots of more architectures that you can use here. So the instant pooling is just getting the latent space output and do a pooling and then classify on top of that. The global classifier, what we mean is you get the output of this latent space, then pass it to some dense layer and pool over that and then classify. And the local classifier is doing classification for each chunk and then do a pooling and then get the results. And there are lots of more like options that you can do for the classifier. So far, the local classifier was the better performance for us, and this is somehow the conclusion of what we have here, like for creating the very first credit modeling, the credit bureau modeling. Lots of things to do for the next step. So we can also have custom tokenizer just in parallel with what we have here as credit story. So we can have both these things together. Also, we can work on modern architectures to use different combination of layers or different combination of technologies. And also the classifier itself can have different architectures here. And this is an open research problem right now, and this is the very first LLM credit risk modeling, so we can build it together. So if you're interested to collaborating in each part of this model, just feel free to reach us, and we can have like an open research problem together and go a little bit deeper to all of these contexts and build like the first cutting edge credit risk model together. On some question that we have also as further research areas here, the model architecture itself has lots of things to do. So we need to do lots of research to get the better performance out of that, and we create a better model architecture here. The second important thing is the data here is temporal. So, and this is really important. You can get, we need some, let's say, architecture here to capture this temporal behavior better. So we can work on this aspect of the data. So this is also an important thing. Custom tokenizer, lots of different ways to deal with that, and it's still an open problem here, how you define your credit, custom tokenizer, and vocabulary. And the most challenging part here, and I would say a very big research question that we can work on here, is explainable AI. So how, because this is a credit problem, so you need to explain this, the results, like the output of this model. So explainable AI and how you want to create a framework to explain the output of this model to the stakeholders, also another open question. I think I'm out of time, and yeah, hopefully this is my last. Thank you, everyone. And